let's go ahead and, okay, hello, we're back. Let's go ahead and do an example. The example being let f of x, it's not different this time, just for fun's sake. Let g of x equal x squared. Once again, I have to define the domain and codomain. I'm so sorry. Let's go from R to R such that by g of x equal to x squared plus the absolute value of x. Okay, I don't know why you're so much trying to write that, but I hope you plan on write that and mull this over. So this is our function now. So again, we're going to try to decide it's well-defined, one-to-one, or onto, or and or, you know what I'm saying. So let's do well-defined first. So is this function going to be well-defined? Well, remember, well-defined means that for any possible input, there's exactly one output, meaning it's defined everywhere, but it has exactly, it does not have multiple outputs. And the good thing about this is functions will inherit the properties of their kind of sub-functions here. So here we have an x squared added to an absolute value of x. And so let's note that the function, note that x squared has one output for each input in R, and so does the absolute value of x. For every input, both x squared and absolute value of x just give us exactly one output. Let's say exactly one output here. Thus, because addition also gives a single output for each of its possible inputs. G of x, which equals x squared plus x, gives exactly one output for each input in R. Thus, G is well defined. So here's what we're trying to get at here. What's happening is x squared for each possible input, imagine an input, like 1, 2, imagine one. Those are good inputs. E, whatever, because we're all of R. Imagine any input in R. X squared is going to have one output. The absolute value of x is going to have one output. And when you add one output to one output, addition just has one output, right? Like 5 plus 4 is not 9 or 12. It's always 9, right? And so since x squared, x, and this plus here all give one output for every input, that means this whole function combined will just give one output for every input. It's impossible not to. Therefore, G is well defined. Oh, I smushed my well defined. There we go. Just like that. So let's work on to one-to-one again. So do we think this function will be one-to-one? Not likely. Yeah, not looking likely. If you look at it, g of x equals x squared plus the absolute value of x. Why is that important? That's important because notice that g of 1 will equal 1 squared plus 1. Oh, I'm sorry. Wait a minute. This is why I'm confused. I don't want to go from R to R here. I want my domain to be just 0 to infinity again. This time including 0. There we go. Thank you. I was thinking in my head this should be a one-to-one example. Where did I go wrong? Yes. So this function right here goes from 0 infinity to r. That's important because notice x squared, right, definitely has a multiple inputs that go to the same output, right? Because negative numbers square are the same thing as positive numbers square. And similar, I think, with absolute value of x. So for example, g of -1, if it was defined there, would equal -1 squared plus absolute value of 1, or -1. -1 squared is 1. Absolute value -1 is 1. This would be 2. And g of 1 would be 1 squared plus 1, which should also be 2. So if we included the negative numbers here, if this is all of r, then we could find two inputs, -1 and 1, that went to the same output. Therefore, by definition, this would not be well defined. But luckily, I caught my mistake, and we're not dealing with r as our domain. We're dealing with 0 to infinity as a domain. And I believe this will actually be 1-to-1. Why do I think that? Well, I think that because imagine, or really, x squared is an increasing function. The bigger x you plug in, the bigger x squared you get. Absolute value of x on 0 to infinity is a, I wouldn't even need that. Well, we'll keep it anyway, just for fun. The absolute value of x on 0 to infinity is, again, an increasing function. The bigger x you plug in, the bigger absolute value of x you're going to get out. So the point is, it seems to me that if a does not equal b, if you have two distinct inputs, like if a is less than b, then g of a should be less than g of b. So they shouldn't be equal. It should just keep increasing. So they'll never be equal. But how do we prove it? That's a good question. And so the way we prove it is, let's go by the following. Wait 1 second. Yes. So the way we prove it goes by the following. Let's go ahead and say 1-to-1. One-to-one claim G is 1-to-1 proof. So the proof that something's 1-to-1 always goes the same way. You assume that there's elements in the domain A and B, so that G of A equals G of B, and then prove if that's the case, A must equal B. And once you've proven that, you've proven there can't be two distinct elements that go, there can't be two distinct elements in the domain that map to the same element in the codomain, because you just showed that if any two elements map to the same element, they have to be the same. So, proof, assume that G of A, assume there exists A and B in the domain 0 to infinity, including 0, such that G of A equals G of B. All right, then what happens here? Note by substitution. So to the definition of G, this means that A squared plus A is going to equal B squared plus B. Yes. A squared plus A is going to equal B squared plus B. All right. Now let's do some calculations. Or I'll just say by substitution here. So I can use the word note and not feel bad about starting essentially the same thing twice because my 5th grade teacher told me not to. So let's say note A squared plus A equals B squared plus B. We want to eventually get around to showing that A must equal B. That's the whole idea. We want to show A's got to equal B. So what I'm going to do is I'm going to try to factor some things here. I think that'd be a good idea. So I'm going to say, let's subtract both sides by B squared and B. by subtracting b squared and b from both sides. So the b squared and b go away here. We get a 0. And we're going to subtract minus b squared here and minus b here. But notice we can factor this a minus b, a squared minus b squared, right? This a squared minus b squared equals a minus b times a plus b. And that just stays the same. And this is by factoring. There we go. And then we can factor, we have an a minus b here and a minus b here, so we can factor again. Also by factoring. And then, thus, a minus b equals 0, or a plus b plus 1 equals 0 by the zero product property. The zero product property, or you can just put it, but I like to name it. It's the zero product property is a thing that says that if two things multiply to equal 0, one of them's got to be 0. So now a minus b equals 0 or a plus b plus 1 equals 0. Notice we want this to happen. Because if a minus b equals 0, add a b to both sides, a equals b, proof done. But what about this guy? We have to prove this doesn't happen. If this can't happen by elimination, this must happen. So why can't this happen? Why can't a plus b plus 1 equal 0? It's all because of the domain. Remember, a and b come from the domain 0 to infinity, meaning they're non-negative numbers. So 1 plus a non-negative number has to be greater than or equal to 1. The smallest it can be is 1. You can't go less than 1 because you're just adding a non-negative number. And then that added to another non-negative number, again, has to be greater than or equal to 1. It cannot go down, it cannot be less than 1. So this sum has to be greater than or equal to 1. But if it's greater than or equal to 1, it certainly cannot equal 0. So that's what we're going to prove. Note, since a and b are in the set 0 to infinity, we have that. Oh, yeah, by the way, I forgot to mention that this absolute value, it meant something before when there was an R here, but it means something now because for when you're in positive real numbers, the absolute value of x always just equals x. So we're totally fine. Anyway, though, so that's a minus b equals 0, a plus b equals 0. We're back down to here. That's why I got rid of the absolute values here and here, because this doesn't matter on our domain of the of non-negative numbers here. So let's just pretend like it was x from the beginning, because it doesn't matter for our fixed domain. Anyway, note since a and b is in 0 to infinity, a must be greater than or equal to 0 and b greater than or equal to 0. Hence, a plus b is greater than or equal to 0 plus 0, which just equals 0. So a plus b is definitely greater than or equal to 0. And then if we come down a little further, and literally on the right further, a plus b plus 1, which is greater than or equal to 0 plus 1, which equals 1, by adding 1 to both sides. Then since a plus b plus 1 is greater than or equal to 1, a plus b plus 1 certainly cannot equal 0. Therefore, by elimination, a minus b must equal 0, which implies a equals b. So G is 1. So G is 1, 2, 1 as desired. Good. Good. So, yeah. This is how you prove that G is 1-to-1. Again, you just assume there's just elements A and B in the domain. So the G of A equals G of B, and then show A must equal B. That means there's no two distinct elements that map to the same element. Therefore, it's 1-to-1. All right. Now let's do onto again. So onto, what color did we use last time? Was it green? That was pink. Use pink again. Now let's prove onto, or disprove onto. Let's see here. Well, will it be onto? What do you guys think? I don't think so. I don't think so. Onto means that for all y in our domain, which is R here, there should exist an x in our codomain, which is 0 infinity, such that y equals f g of x, which in this case equals x squared plus x. So we think for any real number, we can plug something into our function here to get that number. What about like -5? Whoops, right? -5 is a classic counterexample to this because for any 0 to infinity, for any positive number or non-negative number, x squared is going to be non-negative, x is going to be non-negative, so x squared plus x is going to be non-negative. You can't add two non-negative numbers to get a positive number, at least not in my world. So what that means is that g of x is going to be at least non-negative, probably positive. So it's not going to hit any negative numbers, even though there's a crap load of negative numbers in our codomain. So the range will not equal the codomain. The range will in fact be all the non-negative numbers. So we're missing a bunch. So it's not onto. And so the way you disprove onto is you simply have to disprove this claim, or really prove the negation of this claim. The negation of this claim being there exists a y in R such that for all x at 0 infinity, y does not equal g of x equals x squared plus x. All right, that's how you negate things. Flip the quantifiers, negate the predicate, and we're good. And that's going to be more true because like -5 is a good example. So let's proof that G is not onto, not surjective. Proof. Let's consider y equal -5. Note -5 is in R. This is just verifying that y is actually in our domain here. Next, next, note that, next, how should I put this? I guess we kind of have to prove this by contradiction. Because it all comes down to the fact that this is going to be positive, and so it can't equal -5. But the way we actually need to prove that rigorously is like assume it does work and then show it can't work. Yeah, you know what I'm saying. So assume for contradiction that there is an x in the domain of 0 infinity such that g of x equals -5. So the whole thing we're doing here is I have y was -5, and now I want to show that for all x in the domain, y will not equal g of x. That's how we know it's onto. There's nothing you can plug in to get -5. But to prove that you can't do that, we kind of need contradiction. And contradiction is going to assume that there is some value for which you can do it. That will prove that's ridiculous. So therefore, for all values, you can't do it. that covers this, and we're done. So assume for contradiction, there's an x in 0, 5, or 0 and infinity, just the g of x equals -5. Note, or I should say by definition of g, we have that x squared plus x equals -5. Note, since x is in 0 to infinity, x is greater than or equal to 0. Because x is greater than or equal to 0, x squared, which equals x times x, is a product of numbers greater than or equal to 0. So x squared is greater than or equal to 0. So we have x greater than 0 and x squared greater than 0. Since x greater than 0 and x squared greater than 0, g of x, where g equals x squared plus x, is greater than 0 plus 0, which equals 0. Right? If you have a sum of two things, each of which greater than equal to, this is greater than equal to 0, this is greater than equal to 0, so the sum works out. So g of x is to be non-negative, as we're going to. G of x is to be greater than or equal to 0. And this is a contradiction. Or, lastly, I should say, because -5 equals g of x, we have -5 greater than or equal to 0. Here's our contradiction. -5 is not greater than or equal to 0. Thus, assumption is false. And our assumption was there's something that you could plug in, that there exists an x you could plug in to get -5. So that if that assumption is false, that means for all x you plug in, you won't get -5. Thus, for all x in 0 infinity, g of x does not equal -5. Hence, the claim is true. I'll block it. The claim is true. G is not onto. Or maybe I'll just say G is not onto. There we go. So you prove that G is not onto by proving the negation of what it means to be onto. So proving something's not onto, you show that there must exist some value in the codomain that cannot be reached by G. No matter what you plug in, you can't get it. It's in a hard to reach spot. Okay, so I guess tying this all together, because G is well-defined, it's a function, and it's onto, but it's not one-to-one, so G is not a bijection.